Hello, I welcome you all. The problem reads, the spring is placed between the wall and the 10 kg block. If the block is subjected to a force of 500 newtons, determine its velocity when the displacement is 0.5 meters. When the displacement is 0, the block is at rest, and this just simply means at a time equal to 0, the velocity is also 0, and the spring is uncompressed when the displacement is also 0. The contact surface is smooth, and this means there is no friction. This problem is coming from the Engineering Mechanics and Dynamics 14th edition by R.C. Benam. So we have a block, and there is a force being applied. Of course, this force is constant. The force is constant, and there's a spring attached at the very end of this block. So it means as we begin to push this block in this direction, the spring begins to get compressed, okay, and energy is stored in the spring, right? So the block is going to be experiencing a reaction force from the spring, also called the spring force. So we do have the block like this, and we have two components of force. One is in this direction like this, and the other in this direction like this. On this side, we are going to be having the spring force. We have the force, and this is Fx, this is Fy, and we have the weight, and we have the normal force. Right. So basically, this is really what is happening. So we are pushing this particular block this side in this direction, like so, and as Fs is pushing the block to the right, the spring force is pushing the block to the left, right? Right. So basically, this is really what is happening, and there are several approaches that we can use to determine the velocity, okay, when the displacement is 0.5. Okay, so this Fx is constant, this one is constant, right? But Fs is not constant. This is not constant, right? Because Fs, okay, is Ks. Therefore, Fs is a function of displacement, right? So if we are to draw a graph for Fs, if this is Fs and this is S, so at S equal to 0, at S equal to 0, because this one is Fs is K is the proportionality constant. This one is constant, K. This one, okay, not constant, it's a variable. So this one changes, it's a variable, it changes. Okay, so when S is equal to 0, Fs is 0, so we expect something like so. Alright, let's say, okay, something like that, right? Okay, so, but of course it will have positive gradient. So we intend to solve this particular problem by using two approaches. The first approach, we are going to use kinematics and the equations of motion to solve this, which we did in the previous videos. And in the second problem, we are going to use the work energy principle. Right, so being told that the contact, like we said, is smooth, therefore this means no friction. Okay, right. So then let's draw the free body diagram. So we expect a component of this applied force, vertical component, and the horizontal component like so. And then we are going to have, let's say, the weight of the block as well as the normal force. And as this block begins to move, we are going to experience a reaction force from the spring on the block, pushing it against its motion, right? So we'll have this behavior like this. We've been told that when the system itself is at rest, we don't expect any, the spring itself is uncompressed, therefore we will not expect any force from the spring. Okay, so this we have this force like so. And this force will only come into action when the block or when the spring gets compressed, right? Because right now, as long as as long as the spring is not compressed, then you don't expect any force. So when the block is at rest, no force from the spring. But the moment the spring begins to get compressed, then you are going to have a reaction force from the spring, right? So this is W, this is F for Fy, this is Fx, and this is the normal force. Right, so our Fx is just equal to 500 by 4 over 5, and this is just equal to 400, and Fy is just equal to 500 by the rise, which is 3 divided by 5, and this is just equal to 300. And Fs, which is this is Fs, which is the spring force. This one is just equal to K, which is the spring constant, times S. Okay. Right, so Fs here is the function of S. So as S increases, or as the displacement increases, the friction force also increases because they are directly proportional. Okay. So then let's say we work out this using method 1. And in this particular method we are using the equations of motion and kinematics. Right? Great. So we hope to be able to use this particular little space that we have. So let's apply the equation of motion. So we have motion in this direction like so. So we have our AX. So summation of forces in the X direction, this is just equal to MAX, right? What do we have? We have Fx, okay? So this one is just equal to, what's the spring constant? This is 500 times S, okay? Right, so Fx minus Fs equal to MAX. Our Fs is a constant and is just equal to 400, and Fs is a function of S is equal to 500 S, and this is equal to the mass, which is just 10 times AX. And therefore dividing this on both sides cancel out 1 0 like so. Then this just gives us AX is just equal to a minus 50 S plus 14. So Ax itself is a function of s. Okay, as s changes, Ax changes, which is the acceleration. So the acceleration here is not constant, it's a function of displacement. So as the displacement changes, the acceleration also changes. Alright. So again, if you are not sure of the direction, okay, the direction of Fs, you've seen here we are subtracting because the spring force is applying or is going to be exerting a negative force, okay, or it is going to be in the direction opposite the direction of our applied force. Right. So what do? We found the acceleration. Now we can employ the kinematic equation to determine the velocity. We want to find the velocity when the displacement is 0.5 meters. So we are saying this block is supposed to move from this point 0.1 to 0.2, okay, when this displacement is equal to 0.5. Okay, so that is what they've told us, right? Let me just create a boundary here like so. Okay, all right, so let's then apply the kinematic equations. So I'm going to use this derived equation, which is just ax ds is just equal to v dv. And this comes from the two equations, which is v is equal to ds dt, remember velocity, and a is equal to dv dt, right? And from these two equations, if we make dt subject to the formula, then we arrive at this particular equation. All right, great. We are using this equation because our acceleration is not constant, so we are going to integrate this, right, from s naught to s, v naught to v. All right, what do we have? Our s naught is equal to 0, our v naught is equal to 0, and our s is equal to 0.5, right? This is the information that we've been given. Okay, so this information is what we are going to use. And our ax, we already found our ax, which we are just going to replace back, in there like this. That is our ax, we're just pushing it back there. So with all this information, then we can write this as just 0 to 0.5, okay, and then we have minus 50 s plus 40, okay, ds equal to v 0 to v dv. All right, let's get to this side. And then what we have minus 50 s squared divided by 2 plus 40, okay, 40s. Then we are integrating, we are evaluating this, okay, from 0 to 0.5, right? Then this is just equal to v squared divided by 2. This is the v squared we want to find, all right, and therefore our v squared is just going to be equal to 2, okay, we multiply the other side there by minus 50 0.5 squared divided by 2 plus 40 by 0.5. Okay, so we square both sides, right? We square both sides, and once we do so, then we'll find that our v, which is equal to our v2 or v at s equal to 0.5 is just equal to, so let's calculate this, at s equal to 0.5 is just going to be equal to, where is my calculator? There we go. Alright, so we have minus 15 by 0.5 squared divided by 2 plus 40 by 0.5 by 2, then square root of that. This gives us a 5.24 meters per second. So it means the block, when the block reaches or covers a displacement of 0.5, it will have this particular velocity from velocity equal to speed equal to 0 to speed equal to 5.24. Right, so let me again work it out. So we have minus 15, then we can work out properly by 0.5 squared divided by 0.5 squared divided by, divided by 2 plus 40 by 0.5, okay, by 2, and square root of that, we have 5.24. So we are done with the first approach, which we did in the previous videos. Let's now work with the second approach. Okay, right, I'm just trying to create some space. There we go. So let's go with the second approach, method 2. So let's say method 2. And here we want to use the principle of work and energy. Right. So what is this principle all about? Right. So what is this work and energy principle? So the network is equal to the change in the kinetic energy. And this change in the kinetic energy can also be written as half m v final squared minus half m v initial squared, which is just equal to this initial t final minus t initial. We can also write it as half m v2 squared minus half m v1 squared, and this can also be written as 2t minus t1. Right. And work done is just equal to force times the displacement times the cosine theta, and this theta is the angle between the force and the displacement vector. So work done is the transfer of energy to an object by the force, by the applied force, right? By the applied force. Alright, so in our case here, and this work, the network is just equal to the summation of the total work in our system. So we can say the summation of the total work from 1 to 2. So here in our problem, we do have Fx doing work on the block and F. So we have Fx and Fs doing work on the block. So work due to Fx is positive, right? Because energy is being transferred to the block, and the work done due to Fs is negative because energy is being taken away from the block, right? Right, so let's rewrite the whole equation. So we are going to have Wfx minus Wfs is equal to T2 minus T1, right? So writing this, we'll have Fx, okay, times the displacement S minus work done by the spring is half K then S squared, okay, then this is just going to be equal to T1, this is half M V2 squared minus half M V1 squared. But we know that V1 is just equal to V0, which is equal to 0, and therefore this part is 0. Right, so let's place all the numbers in here. So we know also that S, of course, is just equal to 0.5. Okay, our K is just 500. Our mass is already given here, it is a 10. What else? And Fs is just equal to 400, right? Is that so? So what do we have? So we do have a 400 times 0.5 minus half 500 by 0.5 squared equal to half by 10 V squared, and therefore this is just going to be equal to 400 by 0.5, okay, by half 500 by 0.5 squared, then divided by this, we are dividing by half by 10, okay. Right, then square root of both sides, like so. So what do we have? Our V2, which is just equal to V at S equal to 0.5 is equal to, you can grab your calculators and work it out, 400 by 0.5 minus 0.5 by 500 by 0.5 squared divided by 0.5 by 10, and square root of that, we have a 5.24 meters per second. Right, so here, this one here, I meant 2, right? This is 2. So transfer of energy to an object by their applied force, or by the application of a force. So this V2 is in this direction, and so is this one. I guess we are done. So we have used two techniques or two methods which I'm pretty sure we are already familiar with. And I hope this particular video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next